So this is, I don't want to say that because I'm getting excited. This is a talk about art installations that move. I have a background in mechanical engineering, and I just recently finished a master's degree in product design out in Philadelphia, so I get to do a lot of these projects while I was in grad school where nobody tells you not to spend all weekend trying to turn something on, so I spent a lot of time figuring this stuff out, and hopefully some of these lessons communicate well. So feel free to stop me anytime, ask me any questions, but I'm very excited about interactive installations, public art, kinetic sculptures, and all of that. So what I want to talk about as far as getting things moving are some of the ways you can get things moved, make things move, springs with motors, with gears. I'll talk a little bit focusing on motors, which are pretty complicated to use, about controlling motors. Brief dive into electricity 101, because then it all makes a little more sense. A little bit about powering motors, and then mostly building and prototyping, which I think is a pretty important part. It's where you spend most of the time is here at the end. So some example projects that I've done. A lot of these were during grad school, some of them were just fun projects. This was a project I built for NYU's Stupid Shit No One Needs hackathon, which was a beer selfie stick that pours beer in your face before taking a photo of you. And that is a little brushless DC motor used for that one. This is a little autonomous whale car. This has two motors, one for each wheel, and the wheels spin based on input from the sensors. So this sensor is looking to the left. If it sees something, the motor on the left goes faster, so it turns to the right. If it sees something, it turns back. So that's another example of what you can do with a brushless motor. This project was a large interactive piece we built to raise awareness for Hunger Action Month, which is a national campaign in September. We worked with a bunch of nonprofits in Philadelphia, but these big pedals were pushed open by linear actuators. So this is motor driven, but also spring driven. The springs inside held the pedals when you pulled out. So the linear actuators push the pedals open, and then as they release, the springs pull it shut. So sort of a combination of passive and active driving. This is another hackathon project we built, but it is a kiosk for events, conferences, or hackathons. We built it for the Philly Tech Week in May of 2016, but when you use this touchscreen to select something in a room, you could pick, like, I want to go to this project, and it would tell you where the table was. It's not in this demo, but it'd say, like, it's 800 feet that way, and it would have an arrow. It's more likely like 10 feet that way, because rooms are small. That was a servo motor. Here's an example with gears. This project was supposed to be a camera panner, but it uses this mangle wheel and pinion mechanism, which is a cool way to use one motor that's going forward the whole time. Definitely hacked together with a little solderless breadboard, but it uses this mechanism to drive a simple project. So a bunch of different ways that you can make stuff move. You see brushless motors were used in the first one, and then a stepper motor gives you control over the angle. So it's individual steps that are measured inside of the motor, so it has an encoder. So this thing had a stepper motor, so we could say what angle the compass was pointing. A linear actuator is actually a worm gear, but it spins and pushes something out, and then it can actually retract as well. So this is a linear actuator. This thing also had springs. Another example that I don't have anything to show for, but pedal power. You can have stuff powered by people, or it's a small creature pedaling. A solenoid is another electric component that is actually a charged capacitor, but you can have it shoot a piston. So this was a little project we made that shot a golf ball. That was in a robotics class, but you power up the solenoid and then it fires out. So that's another example of the way you can make things move. So, yes?
What's a worm gear?
A worm gear, I don't have a diagram of it, but as you spin, so imagine a long threaded shaft, and then as you spin a gear that's beveled, you're pushing that shaft forward. So it's converting motion 90 degrees. But a nice thing about a worm gear and the way that the gears lock or intermesh is that it's self-locking. So if you try and push back on a worm gear, it doesn't back drive the motor. So it sort of has to do with the gear angle, which is why it's called a worm gear. But it's essentially just turning, I guess you could imagine like an egg beater that you spin the handle on. It turns that motion into like Oftentimes it's a 90-degree angle. A worm gear is like a more complicated version of that works well. It's essentially like the insides of the linear actuator. This is an example of a motor. So the most common used motor is a DC brushless motor. A brushed motor is all mechanical, and inside of it you actually have pads slipping past each other so that when your contacts, it's really hard to explain, which is why I'm only showing this in a diagram, but it switches the polarity and it keeps itself spinning. They're a little bit of a pain to maintain and they can wear out over time, whereas a brushless motor has a bunch of different magnets inside of it. It's a more complicated design, but it also has a control circuit, and that's the exciting part, control circuit, because that means if you power it one way, it'll spin, for instance, clockwise. If you reverse the power, it'll spin the other way. Introducing some circuits to you guys. Here is an example, poorly drawn by hand, of a circuit with a motor. The M is for motor. Now if you have 5 volts potential on the top of the motor and then you connect the other side to ground, that motor will spin. So the simplest version of a motor being controlled is with an on-off switch. So you just disconnect it from 5 volts, this motor won't spin, it has no voltage, it has no potential. So in your simplest version, which is actually what I use for the beer selfie stick, I flipped the switch and it started the motor spinning, and then it stopped the motor. So that's a really easy way to do it, and this is the complicated thing of what's happening inside. Now what's exciting, as I said, about those DC brushless motors is they can go both directions. So in another simplified universe, with a series of switches, just like you saw before, this on-off switch, you can use 4 switches to control the spinning orientation of the motor. So this is possible to do with circuitry, but if you had 4 different on-off switches, you could change the way the current flows so that the motor is either spinning here clockwise or open 2 switches and close 2 switches and it goes counterclockwise. Does that make sense to most people? All right. Cool. This is really just to understand what's happening, and I'll show you this in action in a second. Bear with me here, Electricity 101, this makes a lot of the other stuff more sensible if you at least get the simple concepts, and I'm sure many of you understand this or have heard this before, but it helps me to push my analogies on you so later I can use them again. So current is a quantity representing the rate of flow of electric charge measured in amps. So here's an example where the current is, this isn't actually water, it's electrons. So it's flowing through here, and the flow is the current itself. So as it travels through a pipe or conduit, like a conductor. So current and voltage are the 2 big concepts here. Voltage is the electromotive force or potential difference, usually expressed in volts. And it's sort of like this potential energy, but it's a different concept. This is just voltage. So you have this backdrive of this energy wants to flow through, so it's pushing your current through, essentially. And then resistance, another little concept here to throw in the mix. Resistance is essentially, so it's the degree to which a substance or device opposes the passage of an electric current, measured in ohms. But one example is a constriction in your pipe. So this constriction here will change the flow of current through it, and it can reduce the speed. So if you have a pipe and it's just trying to like blow a bunch of water out into your kitchen or whatever, if you have a constriction, that can slow the flow down and make it easier to use that. So the analogy then to electricity is if you have way too much voltage or current going through, you could burn out a resistor, you could burn out an LED, you could blow some stuff up, burn out your Arduino, but with resistors you can control the current. Now the last thing, the power formula. Power is the amount of energy transferred per unit time, measured in watts, and power is the voltage times the current. So here's an example where we have the same power, but with different voltage and current. So here we have a larger potential, let's call this like 10 volts, and then we have a current, let's call it half an amp, because the pipe is a regular size. Now this is a larger pipe, but less voltage. So if we had 10 volts and half an amp, so we're at 5 watts. Here we might have 5 volts and 1 amp, and we're still at 5 watts. So you can get to the same power, you can do the same amount of work, but sort of like biking. If you change the speed of your bike, it might be more difficult to get up a hill, but you'll still get there, you'll just be pedaling at a different speed. Now
back. Steal your slides?
What's that?
Can we steal your slides?
Yeah, you can have these. These are
Oh,
my beautiful drawings from yesterday or something like that.
I never heard it explained this way. It makes a lot of sense.
Yeah, there's another good analogy of this with skateboarding that you guys can check out from an artist that also teaches in New York. So back to motor directions. Why does this matter? Well, let's give you an example of an H-bridge. Yeah. So I've got a circuit here. This circuit, let's see if I can get this to work.
And that's high tech.
There we go. Yeah. So this thing here is the H-bridge. There are a lot more pins than you think there need to be. I agree with you on that, but this essentially, through a bunch of little transistors, is able to do what that switch does without you having to open and close 4 switches. So, real quick, I'm going to show you this linear actuator. And here I've got, here you can see my 9-volt battery. And then this is my power switch. So if I turn that thing on, let me actually show you this guy. So using something that I plugged into the wall to cheat for a second, if we plug this into the power, you get a linear actuator spinning probably clockwise, and it's pushing this piston out. Now, if I switch the orientation and just swap which pin is in, then it retracts slowly. So the way to do that without having to actually unplug and plug in your pins is you can make a circuit. And this button here actually is a little complicated as a circuit. You can get Spark Fun boards that are simpler, but these are the things in my house. You have an inverter that inverts the signal so that one pin tells it to open and one pin tells it to close. So if I turn this thing on, my 9-volt could have died. If you try it with 5 volts, it'll just happen really slowly, which is okay. Oh, we need the 5 volts. So another thing about voltage is it's a pain in the butt because this IC actually wants 5 volts for power, but the motor wants 9 volts. So I've got this 5-volt power supply. I'll explain a little bit more about how you get power, some of your options there. The 5-volt power is going to the IC and the inverter, hex inverter, and then the 9 volts is going to this motor. So here we got this thing is extending, and then if you press this button, it retracts. So this is all happening through the H-bridge, but what's really awesome, what's really great is that you don't have to make a really complicated circuit, and you don't have to unplug everything manually. So it ends up being really simple, and you can drive, like we did here, the 9 volts separate from the logic that's happening. So that's that. Let's see if it's better. This guy. All right, so that's an H-bridge example. This, which would be really simple, is happening inside of an IC. It gets a little more confusing with voltage. There are lots of good tutorials for how to wire that stuff up and then existing boards. So as far as powering motors, you already saw 2 examples of this, which was a battery holder, as well as a power supply, which is plugged into the wall back there. Other options are springs or mouse traps. Maybe you guys have seen a mousetrap car, or you built it in high school at some point. You can have power supplies. These things are awesome, and you're able to spin the knobs to change how much voltage is coming out, which is pretty handy, as you saw, between 9 volts and 5 volts. It can be a little bit of a pain. Capacitors are another way to power stuff. They can hold a charge, and people have built really fancy quick charging batteries out of capacitors. That gets a little more complicated, but it is an option. Down to motor selection. As I said, there are a bunch of different types of motors. but it's really important that you look at the specs on motors when you're using stuff. If you don't want to dive out into the world of every motor that exists, there's a lot of stuff on SparkFun or other sites where you can just grab off-the-shelf motors. But even then, you want to check things like what is the voltage, what is the current it's going to draw, and then that'll end up telling you the wattage. So that goes back to your power supply, because while this thing may be able to supply 10 watts, your little battery pack or even that supply I plugged into the wall is limited in how much power it can output. So stepper motors, there are a lot of good options out there. Actually, a stepper motor is what they use in most printers. So if you don't want to spend $20 on a stepper motor, you can go take apart a printer that somebody's throwing away, because there are tons of dead printers all over the place. The Pololu motors are really nice. Pololu motor is what I use in your selfie stick, as well as the little whale robot. This is a little lower power load. They're smaller motors. This is easier to supply. But you can imagine something like this, if it's trying to do a lot of work, if it's trying to spin something with a lot of resistance, it can burn out either your wires or your resistors or something else. So this power number then trickles down to the components you select. So if you're making a complicated circuit, you have to know how much power you're working with to select. So this here is a linear actuator that I use. This thing is pretty powerful. It's a very nice linear actuator. So the stall current, just throwing in a term for you guys, is the point at which the motor can't do any more work. So if you're powering it with 12 volts, once it pulls 650 milliamps, that's it. So whatever 7.8 watts converts to in pounds force, that's how much this thing could push up on. So this little linear actuator is actually pretty strong. Those pedals with the springs on them and everything, that pulling on the top of one of those pedals felt like 10, 20 pounds of force. So this thing can do a lot of work, but it also requires then a good power supply.
Excuse me.
Yes.
So that has limit switches to determine when it's at the extent of its range.
Yes.
So it automatically shuts itself off.
It does, yeah. So this, you're right. You got that. This is a limit switch, and it tells itself not to keep driving in. Right, with a worm gear, if it didn't have a limit switch, it would just push the gear right off the end, and that would be a problem. So sometimes you get a simpler motor, and then you have to add your own limit switch or some kind of encoder to know. Or even, something spinning around. Like the stepper motor I'll show you later, you want to stop it before it crashes into itself, so you have to add in some check.
Yeah. So also some of those motors come in with like a torque measure, which is also an indication of the amount of mass it can move.
Yeah.
I was wondering, how do you make sense of that? How do you look at a motor and like, when you look at it and like, yeah, that's going to be able to do the job like I need it to do. I feel that's one of the things hard sometimes.
Yeah.
So when you want to make this thing move, and then you look at motors and oh yeah, it has that much torque with that much wattage, but how do you what's your mental calculation?
So you end up drawing a really simple free body diagram. So this is the mechanical engineering side of me. You can simplify it down. So for torque, you're calculating force at a distance away from your rotation point. So if you simplify it to, for instance, the torque that we needed on the big flowers, that was just looking at how much force we had to pull. Well, actually, we kind of worked in the inverse because we kept adding springs to it. But you can figuring how much force I had to pull with at the end of the flower. So there's like a pivot point. There's a whiteboard somewhere. But you can calculate that torque. So my force times the distance is going to be the same number as the force times distance over a shorter distance. So torque, for instance, like a long moment arm, just like the way a wrench works, you get more torque. So the force with a short arm had to be much more for the linear actuator. So you just do a little simple calculation, and that helps you like ballpark the number, but then you end up with kind of like variations on it. So you can do some math, and most of the times if you can think of a simple version of your problem, like you can end up Googling to find some example where someone did the math for you. And if you simplify it enough to use numbers in their equation, just throw in like a factor of 2 or 3 of safety, which means whatever the torque they say, multiply it by 3. And if you have that much in your motor, you're going to be okay. The other thing you can do with a lot of this stuff, I mean, these Pololu motors are like $15, $20, just get one. and then you try it, and if it doesn't work, you get another
Because
motor.
usually that's the thing, right? If you try to do something too big with one of these and you can shove them up right away, they're gonna.
Yeah, they'll hit the stall current, and they won't be able to go any further.
Okay.
Yeah, so
That's-
they're not gonna explode, they're just gonna not do it.
I've had bad experiences with some others.
No, right, but you can also break them, but if it's a,
Yeah.
you know, if it's a little dinky motor and it breaks. So that's kind of like a fake answer, but.
I mean, I never tried this linear actuators.
Yeah, these are sweet, I like these things. This is $70, but it's worth it. We had one extra and we burned it out in our testing, and then we never had to replace them while they were installed. And that thing was up for 6 months, so through rain and shine and everything. Any other questions on motor stuff on me?
Well, yeah, so the stall current, it's pulling that current and then it tries to push the thing.
Mhm.
So then if it pulls more than one, that's when it stalls.
So it will not pull more than 650 milliamps.
Okay.
Is what, yeah, so it's saying that's the most it'll pull, and at that point, if it needs to do more work, if it needs more power than that, it just won't do it. So the motor will stop spinning. Yep.
I'll ask the question
Okay, so back to powering motors. So we talked a little bit about the current that you need in milliamp supplies. So an Arduino has output pins. So some of these pins from your little microcontroller can power stuff, but they can't power very much. And it depends on the board, I don't remember the exact number, but it's something like 100 milliamps or maybe even less. So if you try and run a motor directly from your Arduino, you'll burn it out. And what you can do instead is build a MOSFET circuit. And I won't go too much into this, but you essentially have a protective circuit so that your Arduino is just turning on and off a switch, sort of like that switch I showed with the motor. It's just plugging and unplugging the connection between your motor and ground. So a MOSFET circuit, check it out, is really nice for driving a motor that needs a lot of force. If it's a smaller motor, you can get away with driving it directly from the Arduino, which I'll do in a second. Here's an example of prototyping. So I'll show you. So we made a little prototype that was controlling a set of servos holding a phone. I'll show you that in a second. But the simple version of it, we built on a solderless breadboard. So you want to defer soldering as long as possible. Soldering is really great and really helpful for prototypes when you don't want them to come apart. But when you have to debug and unplug stuff, solderless breadboard like this is really good for figuring out your circuit. So that was the more complicated version. It was actually a RF antenna because we had the like wireless remote. But I'll show you. Let's see. I can show you this either in real time or I can just load some code. But let's get an example here where. So for a servo motor, which is what I have.
So the last couple slides after the example with a solderless breadboard and a little bit of Arduino code, which devolved a bit into troubleshooting code, was showing off what you can do when you make when you build up your project with a solderless breadboard. This was a project we built using 2 servo motors to move a phone around for filming or showing someone's face. But it was a lot that you could do with just a solderless breadboard that you saw before, this thing here. Another really good thing to use when you're making prototypes are connectors and heat shrink. During my demo, writing that code and trying to plug the servo motor into my little solderless breadboard, the wires kept coming undone, and a connector like this 3-pin Molex connector would work really well. It's really nice to have positive retention You can see this guy has some hooking features to the connector, so you make sure that you get retention if you pull on the cables, especially if this is going to be touched by anybody else or even bounces around in your backpack. It's pretty easy for stuff to come undone. Heat shrink is a really cool technology. You put heat shrink around your wires and you heat it up and it shrinks, and it will keep stuff from touching that you don't want to touch, and it'll also just help with keeping all your wires under control. So you take some of your loose ends, and after you've connected them, soldered them, however you have them in your connectors, you can put on heat shrink and it keeps stuff under control. The working with stranded core is really good advice. Stranded core wire is what you see in this bottom right corner. That wire has a lot of individual pieces, so it's a lot less likely to break if you use solid core wire, which is really easy to put in a solderless breadboard and really convenient. In practice, it can break. If you bend it a few times, you can get a break just in the middle of your length of wire, and it's really hard. It's really hard to debug and figure that out if you build something and all of a sudden it stops working. There are a lot of wires to check. So stranded core wire, really good idea. Here is the advice that I wish someone had gave me early on. For building an installation, there's a lot of lessons I've taken away from them, but some of the simplest here are: first, to decide what you want to do. So if you can clearly write what function you want performed, if you can clearly lay out the bare minimum of what your art piece or your installation is going to do, it's really helpful to come back to it at 2 a.m. in the morning when everything else is breaking to make sure maybe the bells and whistles aren't coming out, but you're going to make sure that function is satisfied. The next criteria is figuring out the environment. Are you going to be inside? Are you going to be outside? Are you going to get rained on? Is it going to be really hot? It's going to be really humid. And power outlets, will you have access to them? If you're trying to run this off a little battery or a generator, that really changes your power requirements, because if you're trying to run this off 9-volt batteries, it's not going to run for an full 8-hour day. And then another question is, will people touch this? If people are going to interact with it, it's a totally different design spec, and you have to think through how many times people will press buttons or what kids will try and break. And the last piece of advice I have is to keep it simple. You're definitely going to have to debug and fix parts of your installation, parts of your project. The fewer components you have, the less that you can have break. And I found this to be true in almost every instance. You may have a lot of other cool things you can add lights, you can do all these other things, but the fewer pieces, the fewer things there are to maintain. So that's good advice. And then also consistent wire colors. If you're gonna end up soldering a board and you have to replace a wire, you have to figure out maybe in the middle of the night, maybe under pressure right before something launches, what is going on or what is wrong. Using red for hot, red for power, black for ground, that's what I do. Other signals, if you have them the same color, if you have your wires consistent, it's a lot easier. And then a backup circuit is always a good idea. And another lesson is, if you have a backup circuit, you pretty much always use it. So it's really nice to make, because if you're in the middle of a 2-week push to finish something, at that moment, everything's fresh on your mind. So if you build another circuit then, it'll be a lot quicker than a week down the road, or when you're in the middle of some other logistical challenge to try and get yourself back in that mindset. This is a little exercise in thinking about a project that I want to build, which is a big gesture writer, which is a large piece where people stand in front of a camera and move around, and it translates to drawing on a large canvas. So there are a bunch of different ways to do this. The audience at my talk had some feedback, but the ideas that I found and kind of put together are using cross beam arms. So this in the top corner is just like a 3D printer or even a plotter. You have 2 axes and you have stepper motors. So thinking about what motors you'd use, stepper motors would be good for that. For control, you could use DC motors if you wanted this thing to run really quickly, but if you use DC motors, you'll have a lot less control over the accuracy. This hanging plotter is a project that's on Arduino. There are tutorials on Instructables for how to make an Arduino plotter, and these spools in the corner are pulling at wires, so this thing is moving in XY, but it's kind of moving along the hypotenuse in XY. And then another way more complicated idea is using this 40 degree of freedom arm. You have just a writing robot. There are a lot of other awesome resources out there. The analogy of water as for electricity was not my own, and I also took inspiration from Tai-Yun Choi at NYU's. He teaches at the School of Poetic Computation. He has a really good article kind of explaining electronics for artists. This book here, Making Things Move, was really good as a guide, and it's actually written by an author who taught at NYU's ITP program, which is a really great program teaching engineering concepts to artists and teaching artistic concepts to engineers. There's also some really good stuff on SparkFun. They have some advice on selecting motors. As I said before, MOSFET circuit is really good for using a microcontroller to drive a motor. And this is an article here on how to do that, giving you an example circuit. Really simplifies that because figuring out MOSFET's kind of its own thing. And then if you are planning to build stuff and you're planning to solder, soldering is an art unto itself. It takes a lot of time. I've definitely had many hours of headaches trying to fix things that I didn't solder well or contacts that weren't well connected. So watching a video and just being sure things are clean, and then you properly add the solder on both sides of your connections. Anyway, watch this video. It's really nice. It's good to just have an in-depth brief or review of soldering, because there's always concepts you can learn again. And finally, I just want to say electronics are a labor of love. This is an example of me building, it was actually my last job, but building up a power distribution board using a printed circuit board. Side note here, if you do want to make complex circuitry and you're going to make more than one board, you can do it on a computer and have somebody print it out for you, and they can make you 3 or 6 or 10. And it's a lot easier to reproduce these than to solder a bunch of cables over and over, and you just have to add the components on top. So actually on the right, this is a soldering iron. This is a heat gun. Oops, this is a heat gun that you can use to solder components to a board, a printed circuit board that already has copper on it, so you just add the solder paste and put components on. But right at the end, I was touching it up with the soldering iron. Electronics are a labor of love, but there are a lot of really amazing things you can build if you put the effort into making stuff and making art that moves. So, thanks again.